All right, welcome to the control room. This is your first day, so we're going to skip the textbooks. Instead, we're going to talk about how this place actually works. I want you to think of it like a three-legged stool. Everything, and I mean everything, has to be in perfect balance. We're going to dive into what that balance means and, more importantly, how you keep it when the pressure's on. You got it. Because theory is one thing, right? But in here, you have to feel how these systems breathe. You need to get how they behave in the real world, because, in the real world, the stakes are just a little bit higher. So pull up a chair. This is your spot now. As an instrumentation engineer, your number one job, the thing that everything else hinges on, is maintaining system balance. It sounds simple, I know, but trust me, every single thing in this plant depends on you getting that right. Okay, let's start with section 1, the homogeneous system. Look, before you can fix a problem, you have to know what normal looks like. For us, we call that a homogeneous system. It's basically the baseline state where everything is just humming along perfectly in balance. This is our goal on a nice, quiet day. And these are your tools, your three main controls: the steam valve, the fuel valve, and the air valve. Remember that three-legged stool I mentioned? Well, here are the legs. The thing you gotta remember is you can't touch one without thinking about the other two. They are all connected. So when we're in this nice, balanced state, there's no net change in the plant's output. Everything's just stable. And that AX equals 0 you see there, don't let the math scare you. It's just the engineer's way of saying all is well, the system is stable. That's it. And here is the golden rule for that stable state. Any tweak you make to steam, which we'll call X, fuel, Y, and air, Z, they all have to cancel each other out. They have to add up to 0. Think about it. If you push one way, you have to pull another way to keep that stool from tipping over. Now here is where it gets interesting. This rule, it actually gives you a ton of flexibility. Let's say you need to bump up the steam for some reason. You can totally do that, as long as you back off the fuel and air to make up for it. See? These aren't chains holding you down. These are your operating modes. This is your playbook for keeping things stable. All right, section 2. The particular solution. Now, of course, a power plant doesn't just sit here running for fun. We have to respond to demand from the grid. And speaking of which, your manager just walked in. He's got an order. So much for our perfect balance. And there it is. Simple, direct. Increase output by 3 units. They don't care why, they just need the power. The how, well, that's our problem now. And our nice, comfortable little rule about everything summing to 0 just went right out the window. So the whole game has changed. We're not trying to keep things at 0 anymore. Now, whatever adjustments we make to steam, fuel, and air, they have to add up to 3. The goalposts have officially moved. So what's the simplest way to hit that new target? Well, you could just crank the steam valve up by 3 and leave the other 2 alone. Boom. X equals 3, Y and Z are 0. It works, it gets the job done. That one single direct fix, that's what we call a particular solution. It's just one specific way to solve the problem. On to section 3, the general solution. But listen, and this is maybe the most important lesson you'll learn today. Running a real plant on one single rigid setting is dangerous. It's asking for trouble. You need options. You have to combine that new target, that's our base setting, with all those little balancing adjustments we talked about earlier. And that combination, that's the general solution. And this equation right here, this is the whole magic trick. It's the full picture. Look at it. That first part, the 300, that's our particular solution. That's the base setting that gets us the output we need. And that second part? Hey, we've seen that before. That's our old friend, the homogeneous solution. That's all the balancing adjustments we can make on top of our base. Let's just put it plainly. The base setting, that 300, is what makes the manager happy. It hits the target. But the flexible adjustments, that's what keeps the system from tearing itself apart while you're at that new target. One gives you output, the other gives you safety and control, and you absolutely cannot have one without the other. All right, section 4, why does any of this matter? Let's bring it all home. Why did we walk through all this stuff? Because this isn't about passing a math test. This is about how you do your job without things going boom. It's about your operating flexibility. This table right here, this is your Rosetta Stone. The particular solution from the textbook, in here, that just means one way to get the job done. The homogeneous solution, that's all your possible fine-tuning and balancing moves. And when you put them together, you get the general solution, which is literally the complete map of all safe operating conditions for this plant. So here's the bottom line, the thing I want you to remember when you go home today. You never, ever, ever run this plant on just one fixed setting. That's brittle, it's fragile, it's dangerous. Instead, you operate within a dynamic range of possibilities, what we call a solution space. That space is what gives you the room to adapt and the stability to stay safe. And that really is what it all comes down to. Understanding this dance between a base target and your flexible adjustments, that's how you keep this whole place running. It's not about getting the right answer on a test. It's about preventing a very, very bad day.
So I'll leave you with this question. Now that you've seen it here, I promise you're going to start seeing it everywhere. This idea of a base goal combined with a whole universe of flexible adjustments, that's not just for power plants. It's in managing a budget, it's in a supply chain, it's even in planning your career. So start looking for them. What other complex systems in your life are actually operating inside a hidden solution space?